quick preview of how polynomials behave. Okay. If you got a polynomial given in this form, it can be expanded using the distributive law, and the steps are quite straightforward. If you expand this polynomial through these steps for equivalent, you get this. Okay, I'm not going to read it to you, you can see what it is. The overall shape of the graph of any polynomial is that of the highest power term. The highest power term here is called your leading term. The power is called the degree. So I didn't use that terminology, but I'll add that. Degree 3, highest power term. If you graph x cubed, which is the highest power term, the leading term, your graph is going to look like, well, the white graph that I had here. Okay, and the white graph comes up like so, levels off at the origin, and then goes back up. The orange graph is going to represent the graph of this function. Now, we see that the graph of this function is going to have to pass through 0 whenever p of x is 0. So, well, p of x is 0 if x equals 7. Okay, most people told me that. And why is it 0 if p equals 7, x equals 7? Because p of 7 is 7 minus 3 times 7 plus 4 times 7 minus 7. Now you easily see that when you look at the factored form and you see you've got x minus 7. Well, x minus 7, if x of 7 is going to give you 0, it doesn't matter then what these other two numbers are going to be. When you multiply three numbers and at least one of them 0, the whole thing is 0. So the 7 minus 7 gives us 0, so the whole thing is 0. People pretty quickly then concluded, okay, yeah, well, the same thing's going to happen. Now, a couple people recognized it and indicated that in the chat. But if x is 3, x minus 3 is going to be 0, so the whole thing's going to be 0. If x is minus 4, x plus 4 is going to be 0, the whole thing's going to be 0. So if x is 3 or negative 4 or 7, it's going to be 0. That means that the graph is going to have to go through the x-axis when x is equal to negative 4, which would be like right here, or 3, which might be here, or 7, which might be here. So the graph for larger values of x, though, for large values of x, x cubed is so much bigger than x squared or x, or any multiple of x squared or x, that those multiples don't matter much. For example, if x is 1,000, x cubed is 1,000,000,000, and negative 6x squared is only negative 6,000,000, which is just 6/1000ths, 6 parts in 1,000 of a billion. And you should understand that. You should think about those numbers and write them out and understand how that works. So if this is a graph where your horizontal scale goes from negative 1,000 to 1,000, of course your vertical scale is going to go up to 1,000,000,000 here and negative 1,000,000,000 here. That 6,000,000 doesn't matter. And the graph won't really look like this to scale, but we're not going to worry about that. We want to get the idea that the graph has to come up from large negative values, go through x equals negative, the x-axis where x equals negative 4, then it'll go up through the y-axis and come back down when x equals 3 to hit the x-axis again, because again p of x is 0 there, and then has to go down and come back up to go through the axis when x equals 7. Okay? A close-up, if we zoom in on this and change the y-scale, it's going to look something like this in the vicinity of the origin. It's not going to go through 0 anymore, because when x equals 0, what's the value of p of x? Well, the value is, you're going to get 0 from x cubed if x is 0, You're going to get 0 here, and you're going to get 0 here. You're just going to have 84. So your x-intercept is at 84, or y-intercept is at 84. No longer at 0 as it would be for x cubed. Well, a lot of other things change in the function, but when you get out far from the x-axis, they don't change much, and the function almost merges with the x cubed graph. We also talked about why p of x is not 0 for any other value of x, and somebody answered on this one. I got an answer. I'm looking over at the chat on the screen. I don't see it. But somebody answered and said, because if x isn't one of these three numbers, then none of these numbers is going to be 0. That's right. The only way any of these numbers could be 0 is if x is 3 or -4 or 7. So when you multiply three numbers that aren't 0, you get a number that aren't 0. You get a number that's not 0. So that the only numbers that are going to give you zeros are these. That means the graph can't go through the x-axis at any other point. So, now down here I say one number must be 0 to get 0, and only 7, 3, -4 get 0. Could have said that a little more properly if I'd had more room to write it. I would say that p of x is going to be 0 only for these values of x. Now let's look at what we got here now. We graph the thing on a scale that only goes like from -10 to 10. If we do that, then we can see more clearly how the graph comes up from large negative values through through the x-axis at x equals 4, through the point -4 is 0, and then up through the y-axis at 84, since p of 0 equals 84, back down to intercept the x-axis at x equals 3, goes down, turns around, comes back up through the x-axis at x equals 7. That's what the graph looks like. Now, to contrast this behavior, we look at another function very quickly, x plus 5 times x squared plus 3x plus 7. Now back up and comment, when you have a polynomial in this form, to get it back in the factored form that we started with is a lot more difficult than going from the factored form to the expanded form. Okay, so you got to do some serious factoring, and even then it can get very challenging. A polynomial, a cubic polynomial with leading, with degree 3, with highest power 3, always factors. Okay, because the overall shape is the x cubed, which goes down to -infinity and up toward infinity. It's got to go through the x-axis somewhere. So it's always got a factor. But it doesn't always have to factor into three linear factors that give you 3 zeros. It can factor into a linear factor and a quadratic factor, where the quadratic factor doesn't have zeros. This factor doesn't have zeros. You can check that very easily if you understand quadratic formula and so forth. The discriminant's -19, so this can't be 0. Discriminant's your b squared minus 4ac. b squared is 9, 4ac is 4 times 1 times 7, 28, -28. Well, it's 28, and when you subtract it, you get a -28, so you get 9 minus 28, which is -19. Doesn't matter what that number is, the fact is that it's negative tells you that you're not going to get a 0 here. There's more than I could say about that, but I don't want to confuse you with more details. Okay, so the only way p of x can be 0 then is if x equals -5, because this can't be 0. This can only be 0 when you get -5, and to get 0 out of the product, one of these things has to be 0. So p of x is what? Well, x times x squared is x cubed, 5 times 7 is 35, and then you've got other x squared and x factors in between that I just indicate by ... that don't really tell you much. Okay, now they do, you know, if you expand it completely, this is what you get, but you don't need this and this. Now if you know calculus, then that becomes important. But for the purposes of this course, really the leading term and the final term are what determine the 0 and the y-intercept. So this function goes through 0 when x equals -5, and this is -5. And when x is 0, p of x is 35, because all the factors other than the 35 will have zeros. If you did this, you can see that. So it's got to go through here and here. It's got to have this overall shape. Well, it starts then maybe close to this graph, comes up through here, comes up here, and goes on and eventually joins up with the x cubed graph. That's one plausible way the graph could look. That's the way I kind of think this graph might look. I don't know yet. I'd have to take the derivative and set it equals 0 and solve the quadratic. I'm not going to do that on screen. Take me a few seconds. Okay. Okay. Another plausible p of x graph. This is a plausible p of x graph. I say, or maybe it could look like this. Still has to go through -5 and 35 here. But it's never going to look like this. It's never going to have more than 2 turning points. And that's important. A cubic graph, a graph of whatever degree, the number of times it can turn is at most 1 less than the degree. Degree 3, it can turn once, twice. Excuse me. Allergy season, can't do much about that. Okay. There we kind of have a synopsis of what we did in class. 12-minute synopsis.